Lewis electron dot structures of molecules. So kind of where we're headed is right, it looks ugly and it looks complicated, but it's not that bad. We're going to actually predict shapes of molecules. And it's kind of a big deal because the shape influences things like melting point, boiling point, fine, but also influences what it would do inside your body. The shape of a molecule has a lot to do with its reactivity. It could make something really poisonous or carcinogenic or be good for you. So there's a lot of information there, and we can get it just from drawing Lewis dot structures. Okay. Here's another. Knowing molecular shape helps us predict where a molecule's electrons hang out most of the time. Let's see if we can infer from this model a few things. Amy, what molecule might that be? It's very common. It's a hint. Water. So you've got the hydrogens and you got the oxygen. So it's bent, and we'll see why. That's coming up in a couple days. But it looks like, Christine, that from this model, the electrons are not evenly shared. I mean, the electrons are spending more time around one element than they are around the others. It looks like they're spending more time around which one? Oxygen. Right. So knowing nothing about how these models are made, it's kind of nice that they make them this way. Oxygen's red, meaning hot, right, or something like that, we kind of infer. So the electrons are really hanging out there much more often than they are around the hydrogens, so they show it kind of blue, and they're not hanging out there very often. This is that whole electron cloud idea, right, that oxygen, and what's really happening is oxygen is throwing in its valence electrons, with this, which is 6. Each hydrogen is throwing in its valence electron. So you end up with 8 valence electrons in this molecule that are used in that cloud. And nobody knows whose electrons are whose. They're just in that cloud. But they're spending most of the time around that oxygen. So we'll end up putting a little partial negative next to it and a little partial positive next to these hydrogens because the electrons aren't hanging out there very often around the hydrogens. Okay? So, but those 8 valence electrons are in there somewhere. And that's kind of where we're getting at. Ooh, is this a visualization of covalent or ionic bonding, Jarixa? What kind of model is that? It's a visualization of...
What would it be, covalent?
It's covalent. Because you have this cloud, right? We're also using the words molecule, right? So, because ionic compounds are like salt, but they're held together by plus and minus. Not only that, they're not a molecule at all. We're not supposed to say molecule. We're supposed to say crystal, right?
For an ionic?
All ionic compounds are crystals. Let's see if I can draw something three-dimensional here. Right, you draw 2 cubes, right? Is that right?
You know how to draw that? That's so cool.
There it is, right? So it's a lattice. It's a crystal. You throw in the sodium ions and the chlorides in there, and it's all held together. Okay? So we are not talking about this. We're talking about molecules. We're talking about this whole electron cloud thing. Covalent bonding, what is it? Well, we kind of already talked about it. All these elements in this molecule are donating their valence electrons, and the electrons are in those orbitals, those clouds, all over the place. What types of atoms form covalent bonds? Alyssa, where in the periodic table are we talking about? Which elements? Not the metals. Everything but the metals. It's the nonmetals. It's the minority. It's all the nonmetals. It's all the nonmetals. Okay, here's an example of a model of a covalent bond formation reaction.
Wait.
Mm-hmm.
Okay, you said all the non-metals, but
Only nonmetals.
A metal?
No.
I mean, sorry, oxygen. Sorry.
Oxygen's
What am I
nonmetal.
thinking about?
They're all. Remember?
Okay, gotcha.
Do you remember the? Well, now you got me going. Now I got to do this.
Sorry.
Okay, so that ladder. I wish I drew in that ladder, right? stinking ladder goes in here,
Okay, that's what I'm thinking about.
right? So here's your nonmetals.
Okay. And then H is an exception.
Yeah. Yeah, so there's all your nonmetals. H is going to be in there. H actually has metallic properties, but it fits in with the nonmetals for some reason. Okay.
Sorry.
And you're good. Keep asking. So here they're saying that each H is donating how many valence electrons, Jesus? 1. That's why it has 1 dot on there. And then it forms H2. Right? Here's my H2. And they're saying it's a single bond. But we're going to draw it like this. So there's my single bond. So it looks like each single bond in this model, Lorna, contains how many electrons? 2, yeah. And we're not, I mean, you can draw it like this, but it's going to be so much easier to draw these bonds like this. It'll look cleaner and it'll look easier, especially for when we get on later predicting geometry. Okay. The octet rule. Big deal. Monica, these elements aren't supposed to be happy in molecules unless they have an octet of an electrons around them. And what the heck, why an octet? Because what's the group number for noble gases? 8. That's why everything wants 8 electrons around it in our structures here. So, is hydrogen, Monica, obeying the octet rule in this molecule that we did? You can look at either one here. It doesn't really matter. Is it obeying the octet rule? Does each hydrogen have 8 electrons around it? No. So hydrogen is not obeying the octet rule. Hydrogen, though, each hydrogen has how many electrons around it, Gilbert? In this model right here, has 2. Right. This hydrogen has 2. This one has 2. They all have 2 electrons. So it's matching what noble gas, really? Helium.
So that's why it is obeying, right?
It is. So it's obeying its own kind of modified octet rule, right? It's the only one that can get 2, because everything else is too many to match helium. But helium's a noble gas. It works. Okay. What is the difference then, would you predict, Victoria, between a single, a double, and a triple bond? What would it look like? Yeah, exactly. There's single. The double bond would have 2. Triple bond would have 3, right? Okay. How many electrons are there, Amy, in a triple bond? 6. Good. Okay. Only atoms of the elements can form double and triple bonds. Christine, did you get this out of the reading? If not, I'll just have to tell you.
Only what?
CNOS. Only carbon, nitrogen, oxygen, and sulfur are going to be playing this game of double and triple bonds. So don't be drawing double and triple bonds between fluorine and anything, right? Because fluorine's not on the list. What does it mean if a covalent bond is polar? Right? Let's go back to our beginning here. Is water a polar molecule? We said this is water. Is it polar? Most definitely, right? We even wrote little partial pluses and partial minuses on here. Right? So it's very polar. What gives rise to a molecule being polar? A difference in, Jerixa, the E word? Electronegativity. Okay, so let's just see if we remember this. What's the most electronegative element on the planet, Alyssa? The most electronegative element on the planet was F. So our arrow went from down there all the way up to the F for increasing electronegativity. So the farther apart two things are on the periodic table, right, the bigger their difference in electronegativity. Shouldn't really pick metals since we're not talking about metals, right? Like two things, like if you pick F and something way over here, right, that's definitely going to be polar. And if you pick F and something right below it, still polar, but not as polar, because electronegativity difference isn't as big. And then in their models, is there any electronegativity difference between those two? No, they're the same thing. So they try to illustrate it this way. It's nice and green everywhere. Everything's being shared equally. There's 99.9999% probability that the electron's anywhere in there. Right? It's hanging out evenly everywhere. But not in the case of HF. Because now F is really electronegative. So there's several ways that the book is going to ask you to do this. They're going to say, draw the dipole moment. For these polar compounds, you draw the arrow towards the most polar element, or towards the partial negative end. You can't draw a dipole moment for hydrogen, H2, because there isn't a dipole moment. So that's the word dipole moment. They might ask you to draw it, or they might ask you to draw these partial plus and partial minuses. And always put the partial minus there by the most electronegative element. Okay?
How do they show like kind of a rainbow?
I like it because we didn't even know why. But I asked somebody and they figured it out. They said that where it's red, that's where the electrons hang out most of the time. So we kind of think of it as hot, and that's where it's hanging out most of the time. Has nothing to do with temperature, though, right? Just has to do with where the electrons are hanging out. It's very unevenly distributed. They're going to be by they have to be by the hydrogen sometimes, otherwise there wouldn't be a bond. But they're going to hang out mostly by the fluorine. Okay, let's skip this first one. We've done that so many times. Let's jump down to this one. Which of the following bonds is least polar? Kimberly, what would you say? Which bond is the least polar? N and N. She saw it. It's kind of a trick question, right? Because they're exactly the same. So there is no electronegativity difference. Indicate the partial charges of the bonds using the symbols partial plus and partial minus. So where would you put, Jesus, on the ClF bond, where would you put the partial plus and the partial minus? Yes. Right? Because fluorine's the most electronegative. Good. Gilbert, how about HCl? Where would you put the partial plus? Which one's closest to F? Chlorine is closest to F, so it has to be the most electronegative, so he has to have the negative, right? That means he would have to have the partial plus. O and O, everybody? There is none, because they're exactly the same, so you can't write anything. Okay. Rules for writing Lewis electron dot structures for molecules. Let's just run through one quick here. Let's say the problem is COF2. Okay, so there's a lot of words here, a lot of steps, but really there's only a few major points you got to remember. So the first one is this, you need to organize this into a molecule, and the first element is in the middle. That's just their convention. So you put C in the middle and just surround it with everything else. Doesn't matter where you put them. All right, they just have to be around the central atom. Make sense so far? So whatever's first, he's in the middle. Hydrogen only has one bond, so hydrogen can never, ever, ever be in the middle, even if they write them first. So hydrogen's done with one bond. And we kind of knew that way back up here. Hydrogen is done with one bond. He's got helium's configuration. He's done with one bond. So hydrogen can never be in the middle. Can never have more than one bond. Okay, so we did this. We placed everything else around it. Let's determine the total number of valence electrons, right? So each element in the molecule is donating all of its valence to the pot. So fluorine has 7, right? So fluorine has 7. The other fluorine has 7. Carbon has, Monica, carbon has 4. And everybody, oxygen has 6. Now I got to do math. 14, 20, that's 24, right? That's 24. So I need 24 electrons on here. Okay. Now everyone's got their own little way of doing this. This instructions do. Here, my little way is just try to get to the easiest answer first, because I just like doing the easiest path. So what I'm going to do is, I know it's a molecule, it has to be connected. Right? There has to be a bond. So I connect them all. And then what I do is I just make octets on everything surrounding the center atom. And man, I might be lucky. I might be done right now. But I got to count everything up. So how many electrons have I used up? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Hey, I had 24. Good deal. But is everything happy? Happy meaning, does everything have an octet? Well, the oxygen, does the oxygen have 8 electrons around it? Yeah, the oxygen does. 2, 4, 6, 8. Right? You count them? 2, 4, 6, 8. So the oxygen's got 8. The fluorines all have 8. Everybody looks happy, but who? Carbon. Carbon only has how many? 6. So then you go back to our little rule. Only between these elements can you form double and triple bonds. So between C and F, no way, because what's not on the list? F. But I can form a double or triple bond between C and O. So since I've got this, let me clean this back up. Clean this up here. Let's clean it up how I had it. Okay, let's go back to where we were. This is where we were. Okay? So since now I'm going to make a double bond between C and O, and my little method of doing it, just erase first, otherwise you screw up by having too many. I erased, so I didn't screw up my total. I still have 24. How many does carbon have around it? Carbon has 8. 2, 4, 6, 8. How many does oxygen have around it? 8. 2, 4, 6, 8. What does the 4 have to do with carbon? That's a good question. It only has to do with the pot, the contribution carbon made to the electron pot. That's all it has to do with. It has nothing to do with the molecule. Okay? So, but everybody wants to have whose electron configuration? A noble gas. Doesn't matter how they get there. Some have a lot farther ways to go. Carbon has a long ways to go. He only got 4 in the first place. Right? So that's the game we're playing. So let's go to the boards and help each other out with this, and we'll get it figured out before you know it. So let's start with Br2. Let's draw the Lewis formula for Br2. I'm going to shoot you with a laser pointer.
What if I do a protest? Like, no going on boards.
Br2, right? So spread out as much as you can. All right? So just start them out. Just write them both, Br and Br. Right? Right, 2 BRs, and then figure out what the total is. Figure out what the total valence electrons are. Yeah, you want octets. How many valence electrons do you have to work with? 14. You've got 14 to work with. So see if it's an easy one.
But isn't BR kind
Everything wants an octet. So connect them, make octets on everything, and see if you have enough electrons to do it. But remember, it's not a molecule unless they're connected. There you go. Nah. Just put a line for a bond. Because, Jesus, I don't even start until I connect them. The very first thing I do is connect them, because I know they got to be connected. And then I make octets on everything surrounding. And see if you get lucky. See if there's enough to do this.
And it has to equal 14, right?
It has to equal 14.
So would you count the little line as just 1, or would you just...
Every bond has 2.
Yeah, so you just count it like 2, 4, 6, 8, and then 10,
14. So do you have 14 electrons in the model? Yeah, this is the answer. Can you have a double bond in there? You don't want a double bond in there. Everything is happy without one. But you can't anyway because CNOS. So we're done. Try H2S now. No, there's not. It's BR and BR. Right? No, H can't be in the middle. So S has to be in the middle. Good. So S has to be in the middle. Jarixa. Whoa, hydrogen, remember, he's done with 2.
That's right. So if you just go like that.
Who's in the middle? S's. Come up and what's your total? See what your total valence electrons are that you have to work with. All right?
Sir. This is right.
How many bonds does hydrogen want? How many electrons do you have to work with? Sulfur has 6. You have 8 to work with, right? All you can have on your answer is 8. You've got way too many electrons on there. Okay. How many does hydrogen want?
2.
You've got 4. See what's wrong with your model? So start with connecting them. Hydrogen's done.
Wait, that one line means
Everything left over goes where? On the center atom. So I used up 2, 4, 6, 8. Right?
that line counts as 2, right?
Yes. So I've used up all 8 electrons. And everybody's happy. Right? Everybody's happy. Okay? Now C, I changed it from your notes. C is IBR2 plus. C is IBR2 plus, not what's in your notes. I think your notes is something else. Oh, it does?
Yeah.
Oh, somebody added something different. Okay. IBR2 plus. 2.
Sorry.
So see what your total is first. Let's make sure we get that total right.
So the I's in the middle?
So the I's in the middle.
So 21.
Okay. Yeah. Now what does this plus mean? I see 21 electrons, right? But it has a plus charge. So it's 20 because it's short an electron. So you have 20 valence electrons. And make sure I's in the middle. And you only have 20 electrons to work with. Because the plus means you're short an electron. If it would have been minus, you have an extra electron. That would have been 22.
Hey, I'm confused.
So how many do you have? How many have you used up?
Well, this one needs 8.
So you're done. He's done. He's done. How many electrons have you used up? 2, 4, 6, 8, 10, 12, 14, 16. How many do you have left over? So put up everything left on the center atom. All right? Whoops, sorry. So can you even be playing the double bond game with this compound, with this molecule? No, you can't. Okay?
You want us to know double bond, but we're not even using it.
You will.
No, I'm kidding. Oh, we will. Oh, you will.
All right? So what I do is I make octets around everything surrounding. Anything left over has to go on the center atom. So I've got 4 left over. I used up all 20. And this is wrong because it has a plus. You have to do the brackets, and you got to write plus.
Now you're adding stuff.
Right? You got to do the brackets and the plus, otherwise it's messed up. So keep going.
We're out of time. Oh, are we?
No, we're not.
No, really? 9:35. It really? Yeah. I was like, what?
We've got we have a long ways to go.
Can we just have a nap?
Come on, hold on. HNO2.
It's like that.
It says it wants you to follow this model.
Me too. I thought they were like telling us.
You better hope your mother doesn't listen to this podcast.
Why? Oh, my mom knows how bad I am. Oh, no worries. I get to see her tomorrow for at least 2 hours. I'm so excited.
I was wondering where you guys were going. Hono, you're going to Hono. Okay. Count up the total. And remember, hydrogen is done with 1 bond.
We don't need to add any.
Hydrogen's done with 1. So you're done messing with hydrogen once you made that bond.
Okay.
Good. Folks are coming up with 18 electrons.
Do you know how much this is?
Oh, it has to be this model. It has to be H, then O, then N, then O again. Now, whatever you draw, make sure you've used up all 18.
Oh, wait.
Okay, now you used up all 18, right? Okay, now you check to see if everybody's happy. Happy, happy, not happy. Right? Because he only has how many? 6. He wants how many? 8. So now you can you play the double triple bond game? Because it was CNOS. N and O, N and O. So you can erase one? There. And now see if everybody's happy. Count it up. Okay. I think you have too many electrons.
No.
You only have 20. Okay, so now you're right. So he's not happy, right?
Yeah.
So now you play. Can you play the double or triple bond?
Yes.
Yeah, you can between N and O. So just erase a lone pair somewhere. And see if you and put it in there and see if everybody's happy. Just try it and count them up now. See if everybody's happy.
Can I just put my dots over here?
Okay. No, then how many electrons do you have to work with?
Yeah.
How many do you have on your model?
18.
No, you don't. Right?
That line you put here,
So
I just put it down.
you've got 18 valence electrons to work with. So if you haven't figured this one out yet, I'll show you how I mess with it. So I'm going to see if I can get my life easy here. How many have I used up so far? 2, 4, 6, 8, 10, 12, 14, 16,
Shall I keep it down now?
18. Right? Because I kind of looked at N as my center atom, kind of. So anything left over, I'm going to end up putting them there. I don't have enough to put an octet on them, but I'm done with 18. So this is my starting point. Everything is on here. Now we can play that game. The reason why we have to play the CNOS game is because who's not happy? N is not happy. It only has how many electrons? 6. So I've got 18 on there. So now if I want to make a double bond, just erase something and move it in. So let's erase, I don't care, let's erase this guy and put him in. Now nitrogen has 8. This oxygen has 8. So it looks like it works. I think there's more than one answer here. Because I could have erased the other one. Let's go back to how we had it. We had this. All right. Let's erase this one and put it in. Everyone's still happy. So I think there's 2 answers for this one. Okay. And we'll find later on that only one of these is really right.
And it's the first one.
No, we'll find out. It's called formal charge.
Ooh, the second one there. And it has like the little thing.
So keep going. Cn minus 1.
So the negative 1 plus negative 1 and you get 10?
Yes, so you have a 10 total. Good. On cyanide, you're going to have 10 total.
Oh, okay. Here.
4 plus 5 plus 1. 10 valence
4
electrons.
plus 5 plus.
See what the folks around you are doing. You have 10. 2, 4, 6, 8, 10. You've got 12. You can't do that. 2, 4, 6, 8, 10. You have 12 electrons. You can't do that. So whatever model you write, make sure you're only using 10 electrons total. And try to make everybody happy. 2, 4, 6, 8, 10. Hey, that looks good. It works, right? Everybody's happy. Yeah, and you got the brackets and the minus. Wow. Alyssa's figured it out. Lauren's got it. Right?
How fast is Really?
Try COBr2.
Do we put it like do we do the linear molecule or do we do?
Well, only if it tells you. Since it didn't say linear or anything, who do you put in the middle? Carbon. Yep. Put carbon in the middle. Mm-hmm. And how many electrons do you have to work with? So make octets on everything. Anything left over, put it on the middle atom. That's the guiding rule there. think a lot of people have figured this one out.
Okay, 2, 4, 6, and then. Oh, I can just do that.
I guess this looks better, I guess, if you put these guys over here, I guess. Very good. Keep going. You're getting the hang of this. Did you figure this out? Okay, you've got not 23.
Oh, no, I'm fine.
I think 4 for carbon. Oxygen has 6. So that's 24 total. Right? So then you made octets around everything. And so you've got 24 used up.
Wait, let me do it again.
You had it.
Yeah, I do it again.
I can't see some of the counting.
Okay.
2, 4, that's 36. So I can go ahead.
And keep going. Finish him. Finish him. Finish him, Monica.
Alright.
Finish him. Make an octet around. Get him done.
Okay, so I can do the
So
O,
2, 4,
right?
6, 8. He's done.
So then I'm 8 O right now.
Okay.
Okay, now that's even.
Uh-huh. Yes, because it didn't say linear. So that means C has to be in the middle. So it has to be C surrounded by an oxygen and 2 bromines. Now this is Cl F2+, not Ci F2+. This is chlorine and 2 fluorines. This is chlorine and 2 fluorines.
So it's all of the sevens.
You need another F. 2 Fs.
That would make things better.
Ta-da!
Mm-hmm. Whoa, you can't do double bonds with chlorine and F.
Why?
CNOS. There better not be any double bonds in that molecule.
How can you? No double one?
No, because CNOS.
But I know.
Do you have enough to do that? Mm-hmm. And then make sure don't forget your brackets.
But C-NOS, that's CL. What are you talking about?
When can you draw double bonds?
Oh, when it's C-NOS. Ah, gotcha. Stupid joke. Just kidding.
You only had 20.
You're tricky.
Keep going if you got this.
Hint in this answer. P for base. Let's see. Here is 5 plus 5 equals 10. No. Oh, it's wait.
When you count, finish. 2, 4, 6, 8.
Right?
Mm-hmm.
Because how am I gonna? Oh, I got it. Just keep moving the frame. Is this?
So you've got a minute to figure out the impossible.
I was thinking of double bond.
P2. P, big,
2, 4, 6, 8, 10.
2, 4, 6, 8, 10.
Is that your only possibility? That might be the only possibility, even though it's not CNOS.
Yeah, that's what I'm saying. That's
Wait.
it. So how does that
So you
happen?
would have to have like a double.
I think you're gonna have to, right?
Because it's too much.
It would have to be a triple because you can't, like, you know what I mean?
Yeah.
Because I'm telling you that it obeys the octet rule. So you're pretty much going to have to be messing with double and triple bonds, even though you're not CNOS, right?
So it's like an exception.
Yep, must
Wait,
be.
Can we just put the dots?
You could try the dots. 2, 4, 6, 8, 10,
And then 1 bond.
12. Right?
Yeah,
Because-
6, 8, 12.
And the reason why we're breaking the octet rule is because I'm kind of telling. So the reason why we're breaking that CNOS rule is I'm telling you that P obeys the octet rule. So you have to work with this until P is obeying the octet rule. P is not obeying the octet rule here. So keep working with it.
Because they're supposed to be 10.
Yep.
And if you put all those dots, it's like 16.
So that's 10 electrons. P's not obeying the octet rule. Yeah, I agree with you. This is the only way you can get P to obey the octet rule.
In total, in the total, it doesn't obey it.
No, because look, right here.
Yeah.
P only has 2, 4, 6. He's not obeying the octet rule. So, man, today's Friday. This week went fast. Have a good weekend. Enjoy your PS.